Good morning, Trini. Have a good night's sleep. Ready to start? Okay, sorry, a bit late. Let us start. Anything you want to clarify?
No.
Okay, let's just review before we start again. Essentially, we are just using this one, this formula, energy of photon, E equals to HF. And you want to convert to lambda, you can use this formula, C equals to F lambda. Okay, today we will be using this one also, the Brody's equation or relation. And then yesterday we went over hydrogen emission spectrum, right, where we see dark background, and then we see color lines, right? Different color show different wavelength. So different wavelength means different frequency. Different frequency means energy is given out. Okay, so this line show energy is given out or radiation is given out. And we observe that at the shorter wavelength is closer together, longer wavelength is further apart. And that's what it means by emission line spectrum. Then we say that to get this line, right, like example, the red one, right, we have this as a ray and then have a reference level. So this is the initial level, and then this is the final level. So electron must move from higher to lower energy level, and electromagnetic radiation is given out. And that electromagnetic radiation is equals to the initial subtract the final one and equals to HF. Then after that, that is the equation. After that, this is what I call evidence. We can observe experimental evidence. Then we need to explain why. Why? We want to illustrate why. So we use classical physics. There's your centripetal force. This is your electrostatic force. So we treat that as equal. And then from there, we get we can cancel the V and get the equation for velocity. Then from the electrostatic, we know that the total energy is minus E squared 8 pi epsilon naught R. Right? So we say this is a limitation. So that's why we have to go to Boyle's postulate, right? That the electron move about the nucleus in circular orbit, and only certain orbits are permitted. That orbit that's permitted is given by the angular momentum. This angular momentum is quantized, right? So it's NH over 2 pi. And it's just a quantum number, 1, 2, 3. And the second postulate will say that electron jump from orbit of higher energy to one of lower energy. Electromagnetic radiation is given by E equals to HF. And after that, from this equation and this equation, we derive the equation for radius. Then after that, we derive this Bohr radius. Right? That's your Bohr radius, and then times n squared. Right? Bohr radius, you put n equals to 1. You want the other orbit, n equals to 2. So today we will derive this equation. Anything you want to ask before we go further? Okay, if not, let's carry on. Okay, I just go very briefly. Right, we started off positive proton and an electron. That's for hydrogen. And then we derive this equation. And after that, there's our potential energy. This is our kinetic energy. We replace the V there with equation. And add these two together, we get our total energy. And then we say that the furthest electron have the largest total energy. right? And then we cannot go any further, right? Because classical physics will tell us that radiation will be given out. But in real life, if radiation is given out, the energy becomes smaller and smaller. And then finally, the electron will collapse into the nucleus. But we see that the nucleus is still there. The element is still there. It doesn't disappear. So that is the weakness. So this person come up with two postulates, right? That the electron move in certain orbit where the momentum is quantized. Right? The angular momentum is quantized. Okay, and then second one will just tell you you go from higher to lower energy level, electromagnetic radiation is given out. Okay, so that's the equation we derive. There's a quantization of momentum. So we square that. Then we replace that v square into here. We cancel all similar factors. Then we get Rn equals to that. Okay, then after that we calculate our ball radius. We put this one equals to 1. And put all the values of H epsilon naught inside there. Right? There's the charge of electron, there's the mass of electron from the value of constant. Then we get that is our radius. That's the ball radius, the smallest orbit of hydrogen atom. Then to find other radius, we just times the ball radius times n squared. So this one you have to memorize faster. If not, you have to memorize this formula. Either one. Okay, so today we start with this ball radius. This is our total energy equation. Remember, this R can change to Rn. Okay, so E square 8 pi epsilon naught, E square pi epsilon naught, divided by R, divided by Rn. So multiply, we take this on top, this becomes bottom. Okay, that one becomes on top. Then we can cancel the common factor, pi cancel off. Okay, e to the power 4, that's your m. And that's your 8 epsilon naught to epsilon naught, so epsilon square, h square, and then this is 1 over n square. N is 1, 2, 3. There's no 0. Okay, any comments so far? Anything not clear? Okay, so that's the total energy for the nth orbit. So the equation shows that the electron can only have certain amount of energy, not all energy, not continuous, right? There's certain amount of energy. We can put 1, 2, 3, 4 here, depending on the orbit it is in. Energy of electron is said to be quantized, right? No more continuous, it's quantized. Only certain value we can allow. So of course we are interested to find where n equals to 1. Right? Put n equals to 1 inside there. Put our value for E inside to power 4 mass of electron inside. There's your A. Then there's your epsilon naught constant value put inside. Planck's constant. Then we get 13.6 electron volt. Remember, this is in electron volt, not joule. Okay, same equation. We have derived that. Right? So that lowest energy, this one, is called the ground state. This is where the electron will be for hydrogen. It will stay there. It will don't want to be in the excited state. Wherever it's in the excited state, it will come down very fast. Energy of 13.6 electron volt is required to remove electron. So that's the ionization energy. So there's the energy of ground state. That's also the ionization energy. So we can replace this one as 13.6, and then negative sign, this 1 over n squared. Then our n equals to 1, 2, 3, and so on. Okay. So Bohr's model of hydrogen atom can also be applied to other atoms. For example, right, as long as it's singly charged helium, it loses an electron, or singly charged, or doubly charged lithium, which is not good lah. It's not a general formula for everything. It's only for those with single electron. The formula for Rn and En can still be used with modification. Right? So if you want to use it for this one and this one, we have to modify it. The E square replaced with ZE square. Right? Because now this is no more E. This is ZE. Right? Where Z is the atomic number of the atom, then we get this equation. If we want to apply to helium plus, or lithium 2 plus. Okay, if you want to understand the equation, how we get that, you can roughly go back to the derivation. Right, so Bohr's model of atom fields in the case of atoms with more than one electron. Cannot apply that, so there's a shortcoming. Okay, I just try to help you understand. There's a formula that we have derived for hydrogen atom, where this for one electron, this for one positive charge, this one negative charge, and then there is for nth orbit. Right, combine these two together, and that one together. Sorry, this yeah, combine these two together, we get this one. Okay, so in this case, if you want to Rn, we have to, if it's for different nucleus with Z electron, then we have to multiply by Z here. We have to multiply by Z here. Okay, that's the reason. And then we have to also, okay, for this part, we have to multiply by Z here. So that's why when we place this one inside here, then we get our Z square E4. Okay, I don't think you need to worry about that too much. It's just application part. Okay, now we try to understand why Bohr give the postulate, right? For your info, right? When you give it out that angular momentum is quantized, there's no other evidence. Maybe he has his own reasoning. But 12 years later, de Broglie proposed that a particle, such as an electron, can behave as a wave with wavelength given by lambda h over p. So if the electron can behave as a wave, it must be possible to fit a whole number of wavelengths into the orbit. So what this is saying is that it's moving in circular orbit, but as long as we can put a whole wavelength there, it will form stationary wave. Right? This is for your info only lah. You don't need to go that far, but just to give you a justification why we have de Broglie's equation, de Broglie's postulate. In this case, a standing wave is set up, and the energy in the wave is confined to the atom. Right? Only progressive wave, the energy move with the progressive wave. Standing wave, the energy stay with the standing wave. A progressive wave would imply that the electron is moving from atom and is not in the stationary orbit. If there are n waves in the circular orbit and r is the wavelength, right? Full wavelength, n times lambda, this is your circumference, 2 pi r in a circular orbit. Then we can rewrite that, take the n down, got that. Then de Broglie's equation, lambda equals to hp. Right? So lambda equals to hp. P is momentum, so it's nv. So we can put these two equations equal. These two. So we get here. Then we can take this mv across there to get our angular momentum, and then take the n up, 2 pi down. That's what we get. Right? Take the nv, the other side, we got this one. 2 pi, take it down, take n to the other side, got that one. So that's the reason. Right? That's the reason why de Broglie suggests Right? It gives you the basis that the electron can be in a particular energy level if it is in a stationary state. That means it forms standing wave there. Electron revolve around nucleus in certain orbits. Each orbit is having certain energy level. These orbits are called stationary orbit, right? Or energy level. The orbit near to the nucleus is having the low energy level or the lowest, and the outer orbit is having the highest energy level. Electron can revolve in certain energy level without losing energy. So if it's in a permitted orbit, then it doesn't lose energy. It doesn't radiate energy, not like classical physics. As long as it is in an orbit, it will radiate energy. So now we have readjusted with Bohr's postulate that as long as it's in the permitted orbit, it doesn't radiate energy. On the addition of energy to the atom, the electron jumps to orbit of high energy. So if it's in N1, receive electromagnetic radiation of the right energy, then we will go to N2 or N3, depending on the energy given. Okay, any question before we carry further?
No, chưa?
Right? Electron transition. Right? We're just reviewing what we have learned. Right? That's the initial energy level. This is the final energy level. This electron in the initial energy level, we call the excitation. When electron move from a higher energy level, EI, to a lower energy level, EF, electromagnetic radiation of frequency F is given out. We are just repeating. Right? You've gone over that again. I, EI minus EF, that's the energy difference between these two. And the energy difference equals to energy of the electromagnetic radiation. Okay, that's how we represent it. Energy difference equals to energy of electromagnetic radiation. Okay, now we are just reapplying this equation that we have derived earlier. Okay, now we can put this one as EI, then EF. Right? Just using this equation, that's all. And then put in this on I. Remember that our E equals to hc over lambda. The energy of photon emitted, okay, we got 13.6. Right? EI, put Ni there, square. Okay, that's our Ni. And minus NF. NF, the same thing, same equation. I said that this become NF. Okay, minus NF. You take the negative sign out. So that's our equation. The next equation that you need to memorize. Any comment or anything that is not clear?
So far, okay.
Right, remember this is in joule. This is in electron volt. Don't get confused. You have to convert to joule first before it can work out. So this one will be in electron volt also. Okay, try this question using the formula that you have just derived. Number 10 in your worksheet. That is the equation that we are using. This one. Tell me the answer. You want to go any further? If we have time, then we start a new subsection. If not, we will do some exercise to reinforce what you have learned. Clarify your problem. Right? Tell me when you have calculated the answer. Got the answer or need help? Okay now. Anything, any problem that you need help? Anything not clear? Determine for hydrogen atom, an electron make a transition from N1, N5
Chair, the answer is 0.967.
0.967. Let's see. Let's put inside there.
Okay.
Initial is 5 and 6. Okay, 0.967. Good. Calculate the wavelength. Trying to force you to remember the formula. Remember to convert it to joule first. Okay, can or need help?
Chair, give me 1 minute, Chair. (1.29 times 10 to the power -6).
Okay, good. Which region of the electromagnetic spectrum?
Infrared.
Okay, infrared, good. Either you know roughly the magnitude, right? If it's visible, it's about 2. If it's ultraviolet, it's about 10. Or you look at this one, n equals to 3. Western series or infrared region. Okay, we have completed. Let's try to do 24.6. Try the question. Sorry, 24.5. This one. 24.5. Which state in the hydrogen atom correspond to radius of 0.8496? Yep. You should be able to use the
4.
form formula that I just given you, you have to calculate out.
Yeah, I got 4, teacher.
You got 4. Right? That's the formula. Memorize it and put in your value. Right? Take the n square down. Sorry, take this one down. R is given there. Change it to SI unit. Okay, good. 4. Try number 2. An electron is in the n3 orbit of hydrogen atom. Calculate the orbit radius.
4.78 times 10 to the power negative 10 meter.
Right? Use this formula. Put your n equals to 3. Okay, good. Number B, part B. The speed. Choose the right formula.
7.27 times 10 to the power of 5.
You calculate at home or you look at the answer?
I calculated it, teacher. Did earlier.
Right? You've forgotten, derive it. As I said, no need to memorize formula. There's too many formulas to memorize. Just go to centripetal force equals electrostatic force for hydrogen. And your V, take your R across, take your M down. That's the equation you derived earlier. And put in your value for E, your R, that's your R. Your M get from the value of constant. Epsilon naught also value of constant. Calculate out. Okay, angular momentum. You got R, you got V. Then you can calculate your angular momentum. What the answer?
.17 times 10 to the power negative 34.
Okay, good. Just replace there's your formula for angular momentum. Mass of electron. Speed, that's your speed. R, that's your R. Okay, centripetal acceleration. You can remember the formula.
V square over R.
Or for angular momentum, you can use this one also lah. Right? Either one, either method. Okay, V square over R. Put your V inside. You calculate your V. You calculate your R. Put inside there. What's your answer?
So I get 1.106 times 10 to the power of 21.
Okay, good. Number 3. Find the energy in electron volt of hydrogen atom in the ground state. Yep.
Negative 13.6.
I've forgotten the formula. As I said, derive it. It doesn't take a lot of time. Right? And then put your momentum is quantized. Angular momentum is quantized, and substitute and get derive the equation. Right? It takes a bit longer, but as I said, too many formulas to memorize. You're going to memorize, you are going to be in trouble. How to? You memorize wrongly, you get wrong answer. Okay, minus 13.6. Let's try one more, then go to another. Okay, I can use this equation. Either one. Okay, number 4.
1.22 times 10 to the power negative 7.
Hydrogen atom is in the ground state. Find the longest wavelength that it will absorb. Right? So longest wavelength corresponding to the shortest frequency is equivalent to the smallest energy difference. Right? You're just using this formula. So smallest energy difference is from your E2 minus your, this is your 1, right? Ground state. So it's 1 point, or you can use, we are just using this formula in electron volt as well. You can convert it to joule if you want it. And after that, use this formula, put in your value for H, C, and lambda, and we have calculated energy for lambda, right, for the wavelength. And calculate out. Oops, sorry. What am I doing? Okay.
Okay.
Any comments so far? If not, let's go to another subtopic. We still got a little bit of time before we have to take a break. Try
No, need to
24.
take break. You can continue.
The others you can do. Let's try 24.6. Radiation of wavelength 80 nanometer is ionized. Hydrogen atom in the ground state. Calculate the velocity of the electron removed from the ground state.
Kinetic energy equals to Hc over lambda minus ionization energy.
Huh? Why you use kinetic energy? So to be using energy of that energy.
No, equate the 1 over 2 mv squared together.
Or you equate to kinetic of electron equals to energy of photon minus ionization energy.
Yep.
And you can subtract, convert it to electron volt. From electron volt, convert to joule. Then that's your answer. Right? The kinetic energy equals to half NV squared. Okay. A bit long.
Okay.
Let's put it to work through. Any comment?
No.
Determine the wavelength of photon that would ionize hydrogen atom in N equals to 2 state and give the ejected electron a kinetic energy of 8.2 electron volt, same as previously. Okay, can get the answer?
Can just.
Yeah, what's the answer?
1.07 times 10 to the power negative 7.
Right, to ionize from N equals to 2, energy of photon required, you can use the same formula. Right? When it's ionization, the final one must be infinity. The initial one is 2 and 2. So you get 3.4 electron volt. And energy of photon equals to energy, kinetic energy of electron plus ionization energy. So 8.2 plus 3.4 is 11.6. Right? That's a 8.2. That's a 3.4. Okay, then use this formula. Okay, that's what we get. Okay, look, anything that you want to ask, the rest you can do yourself. Since it looks like you are okay, we will take 5 minutes break.
No, don't want teacher, can just
You got no
continue.
choice. it will just shut down itself. This time they give you reminder already. In 4 minutes
No,
time,
for
it
me
will,
don't have also at all, sir.
don't know. Mine is still remaining meeting is 4.30.
Okay, okay, okay,
No choice. 5 minutes time we will have to shut
okay,
down. So might as well take a break now.
okay, okay, sir, okay.